SwayamPrabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In the module 17, we will be looking at organic transformations and reagents, mainly chemo, regio and stereoselective transformations. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, Ministry of Education, New Delhi. So in this module, what we are going to learn is basically we will look at some chemoselective and regioselective reactions and reagents, and we will be looking at basically the selectivity between primary and secondary alcohols, or we will also be looking at selective reduction of either aldehydes or ketones or esters or acids in the presence of other functional groups. So these are some of the things we are going to see in this particular session. So let us look at the problem. For the following three-step conversion of A to B, the appropriate sequence of reactions are. So this question was asked in June 2013. So we have a diol that is given as a starting material, and in the product we have aldehyde and another protecting group that is introduced here. So there are two things that is happening, and this is happening over a period of 3 steps, and the combination of reagents are given here. One is manganese dioxide, the second one is ethylene glycol in the presence of paratoluene sulfonic acid, and in the third step we have PCC, that is pyridinium chlorochromate. So these 3 reagents are used for the transformation. In the second combination we have PCC followed by MnO2 and the protection by ethylene glycol, and in the C combination we have PCC followed by protection, then Jones reagent for oxidation, and in the last option we had given Jones reagent followed by protection of protection using ethylene glycol and MnO2 oxidation in the final step. So these are all the various permutation combination given. We are going to see which one will do the right set of reactions. So before we get into how to solve or how to identify the final sequence of reactions, let us look at what each reagents will do. Based on that, we can easily get a clue like how they can be actually placed. So here there is a primary alcohol, there is a secondary alcohol. So the primary alcohol is oxidized to an aldehyde. The secondary or the benzylic alcohol is oxidized to the ketone, followed by it is protected. So these are all the steps that are actually happening, and let us look at each reagent what it will do. MnO2, that is one of the reagents that is given. MnO2 will do allylic or benzylic oxidation of that particular hydroxyl group will be oxidized, and they will be converted to either aldehydes or ketone. If it is a primary alcohol, that is a primary benzylic primary allylic alcohol, or even benzyl alcohol, that will be converted to an aldehyde, and if it is a secondary alcohol, that will be converted to ketone. So this is what MnO2 will do. The next one is ethylene glycol and PTSA combination. So this is generally used for the protection of the carbonyl, whether it is an aldehyde or a ketone, both will be protected using this particular reagent. And PCC, pyridinium chlorochromate, generally used for the oxidation of primary and secondary alcohols to aldehydes and ketone. So here we don't have anything called allylic or benzylic. This is mainly for just primary and secondary. So this is one thing we have to remember. It will oxidize both primary and secondary. And what about the Jones reagent? Jones reagent will oxidize the primary alcohol to carboxylic acid directly and the secondary alcohol to ketone. So that is what is the Jones reagent will do. So that means we have various permutation combinations are possible. Now how we are going to do is we have a benzylic alcohol here. So this benzylic alcohol has to be oxidized first, leaving this alcohol. This should not undergo oxidation, because if this also undergoes oxidation, what will happen is if you are going to use the ethylene glycol protection, both will be protected. So that is the problematic one. We don't want that, because we want the primary alcohol to just undergo oxidation to just an aldehyde, not carboxylic acid. So in other words, oxidation which is very specific for the benzylic or allylic alcohol is the reagent we have to use. So in other words, we have to use MnO2 is the only reagent that will carry out this reaction. So in the first step we will be using MnO2. That gives the corresponding carbonyl derivative. This can be now treated with ethylene glycol and PTSA, paratoluene sulfonic acid. So this carbonyl will be protected as the 1,3-dioxylane, and we still have the free hydroxyl group, and this free hydroxyl can be oxidized to aldehyde by PCC, because PCC will oxidize any primary or secondary alcohol. Okay, so we have a primary alcohol here, then use PCC, then it will automatically oxidize that to the final product. So this is how we can use the reactions in the sequential order. If the primary alcohol is oxidized to the aldehyde in the first step itself, then protection will not give the required product, because we want the carbonyl ketone to be protected and we want the aldehyde to be free. So that is the one thing we have to be very sure how to use the choice of reagent in this particular transformation. The next problem, the most suitable reagent and reagent combination A to C required in the following conversions are: we have a alpha beta unsaturated system having a double bond, an isolated double bond. So this is one type of system. It's nothing but the carbon. So this undergoes three types of reactions, one with A, another one with B, another one with C. So we have three different reagents that we are using that leads to different types of product. This question was asked in December 2013. So in A, what happens is the alpha beta unsaturated double bond is the one which is reduced. Okay, so this is one type of reaction, a selective reduction of an alpha beta double bond with respect to a isolated double bond. So this is one type of reagent we have to look for. And in the B, the carbonyl is only reduced to the hydroxyl group. So that is the second one. So that is the selective reduction of the carbonyl to the alcohol. The double bonds are unaffected, so they remain as intact. And in the C, the isolated double bond is reduced. The alpha beta unsaturated system does not undergo any reaction. So these are all the three different conditions. So the combination of reagents are given here: lithium and liquid ammonia, that is the Birch reduction condition. We have the sodium borohydride and CrCl3 combination, that is the Lucci reduction. And we have hydrogen and ruthenium rhodium triphenyl phosphine chloride. So Wilkinson catalyst is given. So these are all the combinations, three different combinations that are given, and we are also given pelletized carbon and hydrogen combination. So these are all the various combinations that are given, and let us look at what are the each individual reagent will do. So lithium and liquid ammonia, this reduces selectively the double bonds in alpha beta unsaturated system. So you know we have to reduce the alpha beta unsaturated system very specifically here. So we can easily figure it out. This is going to be the lithium and liquid ammonia combination. And the sodium borohydride cerium Cl3, this is the Lucci reduction conditions. This reduces the ketones. Basically, whether they are in the alpha beta unsaturated system or the normal system, it reduces selectively the ketone and not the aldehydes. So here is another condition. In other words, sodium borohydride can be used for this particular reduction. And the next one is hydrogen and triphenyl phosphine rhodium chloride. So this selectively reduces the isolated carbon-carbon double bond. So this is the one that is used here. So you know the three reagents, and of course we cannot use hydrogen and pelletized carbon because this reduces all the double bonds. So we have all the three combinations here, lithium and liquid ammonia for this particular transformation. So this is A, this is B, and this is C. So this is the right combination for the reduction of these systems. Let us move on to the next problem. So in the following reaction sequence, the structure of the product formed is, we have four different products, A, B, C, and D. So we have a bicyclic system. This is an alpha beta unsaturated carbonyl system. If you look at very carefully, most of the reactions, people prefer the alpha beta unsaturated system for various reactions, either for conjugate addition reactions or for reduction reactions or selective reduction of the carbonyl, selective reduction of the double bond. So if you are planning and preparing for a CSIR-NET examination and other thing, focus more on these kind of reactions, like what are the different types of reactions an alpha beta unsaturated system can undergo, because various time, this substrate, that alpha beta unsaturated substrate, is the crucial one for many type of reaction. So focus on that, what are the different types of reactions and how the different reagents can be used to transform various functionalities with that one. Okay, so that will help you clear CSIR examinations, because you can easily understand many reactions very quickly and you can solve many problems. So here again, let us come back to the reaction. So this alpha beta unsaturated system undergoes, the first step is the diol H reduction at in the hexane as a solvent at minus 78 degrees centigrade. So this is step number 1. In the step number 2, we are using a chloroacetic acid is used in the presence of DEAD and triphenyl phosphine. We will see that what this reagent will do. And the last one is lithium aluminum hydride. So the first one will reduce, the diol H will reduce carbonyl systems, esters to aldehydes or alcohols. So basically diol H is nothing but a reducing agent. So that is point number 1. 2, the chloroacetic acid in the presence of dead and triphenyl phosphine. See, this dead and triphenyl phosphine, that is DEAD, is nothing but diethyl azo dicarboxylate. Okay, so that reagent with in the presence of triphenyl phosphine is used for the Michinobu reaction. So in the Michinobu reaction, a hydroxyl is converted to an ester. The only important thing we have to keep in mind is this reaction specifically proceeds via inversion of configuration. So this is one very crucial step we have to remember when we look at dead and triphenyl phosphine, that Michinobu reaction. And what is the last one? Lithium aluminum hydride. Lithium aluminum hydride will reduce the ester or carbonyl group to the alcohol. So this is some idea you can think about. Now if you look at all the 4 products, so what is happening? The starting alpha beta unsaturated system is getting converted to an alcohol. That's it. In A and B, the double bond is retained. In C and D, the double bond is reduced. So these are all the only thing. So now we have to simply look at what diol H can do and what lithium aluminum hydride can do, because lithium aluminum hydride reduces the ester. So in other words, the 4 hydroxyls are formed by the reduction of ester, and if you go one step back, the ester is formed from a corresponding hydroxyl group. Okay, so inversion takes place, and after the inversion we get this final product. So that means, what is the starting stereochemistry of the hydroxyl? Inversion followed by reduction. So this stereochemically we will have to follow this reaction to clearly identify what is the right set of reactions that are actually happening, or the reagents that are involved. So if you look at the diol H reduction, so here the diol H generally reduces alpha beta unsaturated carbonyl to an allylic alcohol. In other words, nothing happens to the double bond. So the double bond is retained. So in other words, if you look at the final, the combination of 4 in the starting material, in the question, we have 2 C and D where the double bond is reduced. So in other words, we can clearly say these 2 cannot be the choices, simply because diol H cannot reduce, or it does not reduce the alpha beta unsaturated carbonyl to the complete reduction. It only gives allylic alcohol. So now the diol H can approach or reduce this carbonyl from 2 different directions, because this is the crucial thing we have to be very careful. The diol H can approach or can reduce the carbonyl from this side, or it can also reduce from the other side. So there are 2 possibilities there. Based on which site of attack, we are going to say what is going to be the product. So now, one is a less hindered site, another one is a more hindered site. If you look very carefully, we have a hydrogen atom here that is pointing below or below the plane, that is one, and we have a methyl group. Now this diisobutyl aluminum hydride itself has isobutyl group, so that is a very bulky group. So if this bulky group has to attack from this side, I think there is going to be some problem. So if we look very carefully, these are all the both possibilities that can happen. One is given from the blue arrow side approach, another one is given by the pink arrow side approach. So these two possibilities are there. But if we look very carefully, this methyl group and this isobutyl group are bulky in nature. In other words, the isobutyl group cannot approach from this direction. It can only approach from the less hindered side or from this blue arrow side. So that is the crucial thing you have to remember. Once you remember, or once you can figure it out, then we can actually say from which direction it will approach. See, it is not the carbonyl group side approach only, whether it will approach from the top or it will approach from the bottom, because it can only approach from one side. It cannot approach from the opposite side. Okay, so the opposite side is actually protected because of the methyl group. There is a steric interaction, so it can never approach from the other side for this reduction to take place. So when it approaches from this blue side arrow approach, in other words, this entire group will be on this side attached to the oxygen. So the hydrogen is now pointing downwards. Because this hydrogen is actually pointing from the downwards, so the diisobutyl cannot approach from that hydrogen side, even though that is the less hindered side. It cannot come and approach from that side of this carbonyl group. So it comes and approach from the top side, and that is how this particular oxygen aluminium bond is formed, and that leads to the hydroxyl pointing above the plane. So this is a crucial thing we have to remember in identifying, because the stereochemistry of this hydrogen atom decides the stereochemistry of this particular hydroxyl group. And moreover, the presence of this methyl group is also crucial in preventing the attack of the diisobutyl group from the other side. If, say for example, instead of methyl group, if there is a hydrogen, then there is both possibility that we may end up with a mixture of diastereomers. We will not get a single product in this particular case. So selectively, the approach of the diisobutyl aluminum hydride takes place from the top side, and we end up with this kind of hydroxy derivative. And of course, we know what is the next step. So in the next step, the treatment with the dead and the chloroacetic acid leads to the inversion of configuration, because this is an SN2 reaction, Mishinobu reaction we have discussed. So that leads to inversion of configuration on this particular carbon atom. So you see the above bond is now converted to the below bond. Then finally, what is the last step? The reduction of this particular ester takes place, which gives the hydroxyl in the below configuration. So that way we can easily figure it out what is our final product. So let us move on to the next problem. So here the major product formed in the following reaction is, we have a diol, alkyne diol is given. This is treated with 4-methoxybenzaldehyde in the presence of acidic conditions, followed by diol H reduction at -78 to -40 degrees centigrade. We end up with 4 different products, A, B, C, and D. And we have to identify what is actually the right product that will be formed in this particular reaction. So when the 4-methoxybenzaldehyde is treated with the diol in the presence of an acid, what happens is basically the dioxazine is actually formed in this particular case. So the 1,2,3 diol is protected as a 6-membered ring. So this is the crucial thing in this particular case. And this protection, once it is formed, what is the next step? The next step is treatment with the lithium aluminium hydride. So this cyclic acetal basically protects the aldehyde group. This benzaldehyde has a aldehyde group. That aldehyde group and these two hydroxyl all put together form the 6-membered cyclic acetal derivative, diacetyl. So now the next thing what we are going to look at is the reaction of the diol H. So like the previous case, in the previous case we have a methyl group which prevented the approach of the dimethyl isobutyl group from the other side. similarly, here also we have two types of approach of this diball H to this particular oxygen, because the diball H actually opens up this cyclic acetal in this particular case. So we have two oxygen because we have a aromatic ring and we have two oxygen atoms, and in one side we have this alkynic side is present, and in the other case we have free, nothing is present. So no substituent on the other side. So selectivity can be used or introduced in this particular case, because one side will prevent the approach of the diball, another side there is no functionality, so the diball can easily approach that oxygen. So these are all the two places where it can actually happen. Because of the presence of this group methyl and the alkyl chain, the diisobutyl aluminum hydride cannot approach from this side. Here I can say this is the right side and this is the left side attack. So in the right side it cannot have come and attack, so it can only come and attack from the left side. So that is how the opening of the ring leads to the required product. Now the R group, whatever I have mentioned here, is nothing but the 4-methoxyphenyl group. That is the one which is very bulky at the top. And once this opens up, we actually can see how the hydrate can be transferred. So the hydrate from the diball H will be transferred to this particular carbon atom. This is the benzylic carbon. So this hydrogen getting transferred to the benzylic carbon leads to the opening of this particular substrate. So in other words, if you look at the overall reaction, we had the diol, and the diol actually underwent protection by the 4-methoxy benzaldehyde, and that dioxylane derivative was opened up by the diisobutyl aluminum hydride to release the highly reactive primary alcohol. So in other words, if you look very carefully about this reaction, we have a primary alcohol, we have a secondary alcohol, and protecting primary alcohol is a very highly efficient reaction, but protecting the secondary alcohol selectively is a more challenging one. So by using this aldehydic acetal formation followed by diball H reduction, we can selectively protect a secondary hydroxyl in this particular case compared to a primary hydroxyl. The crucial thing is we have a substituent on the secondary hydroxyl which prevents the diball H approach of the opening of that dioxylane ring. So this is how we can actually regio selectively open up that dioxylane derivative in this particular case. Let us move on to the next problem. So here again we have two hydroxy compounds. So we have a primary alcohol, we have a secondary alcohol, and the major product formed in the following reaction. The reaction is, the first step is reaction with benzoic acid, DCC, DMAP and DCM. This is nothing but a esterification reaction. We end up with the intermediate A, which undergoes oxidation by pyridinium dichromate DCM followed by alumina reaction. So the alumina reaction is generally an elimination reaction or dehydration type reaction, and PDC and DCM reaction may be an alcohol oxidation reaction. So these are all the two things we have to remember. And if you look at A and B, we have 4 different combinations. So in the first AB intermediate, we have a esterification reaction. So that means either the primary alcohol will undergo esterification or the secondary alcohol will undergo reaction. So if you look at 1, 2, 3, 4, in 1 and 2, the primary alcohol underwent reaction, and in 3 and 4, the secondary alcohol underwent reaction. So you obviously know which one will undergo reaction between primary and secondary. So the primary is the most reactive one. So obviously 1 or 2, that intermediate A is the most preferable or the major product that will be expected, and the 3 and 4 is not. So that means we can completely rule out 3 and 4. Now in the second step, what is happening? We are oxidizing and we are also allowing it to undergo elimination reaction. So what are the two different products? So in the product B, we have a carbonyl group, and in the product, in the second option product B also we have a carbonyl group, but there is no alkene that is formed, because the last step, alumina reaction, generally leads to elimination reaction. So without even looking at the entire mechanism and other thing, we can actually predict in this particular case the product is going to be the first one, because that only is having the alkene, that elimination happened, the product is there, but the B1 has the hydroxy group intact. So when we treat with alumina, dehydration will take place. So that means the hydroxyl group cannot exist. In other words, the combination, second combination, is not the right product. So we can easily, without even looking at the mechanism, we can solve the problem. Let us look at how the reaction actually proceeds, because since we know how the reaction proceeds, I'll quickly go through that. So the first step is nothing but the reaction of the esterification is the overall reaction. So various steps are given here, because this is basically the DCC coupling reaction. So dicyclohexyl carbodiamide based reaction. Here DMAP is used to facilitate that reaction. So the acylation is facilitated by the presence of DMAP in this particular case. So an active species, active pyridinium species is generated when we treat the carboxylic acid with the DCC. So the most reactive species, instead of the simple carboxylic acid, which is less reactive, we have a highly reactive benzoyl group here generated with the DMAP here. So this is the most crucial activated functionality that is formed in this particular case. An activated amide is formed here, and this reacts with the alcohol. So as I mentioned, we have the primary and the secondary alcohol, both are present in our starting material. So the primary alcohol undergoes reaction very selectively. In other words, we end up with this particular ester that is formed as the intermediate A. So once the intermediate is formed, what is the next step? We are treating that with the PDC, that means pyridinium dichromate, that oxidizes the secondary hydroxyl to a ketone. So that is also fine. And now alumina based dehydration, here in this case elimination reaction actually takes place. So we have a beta hydrogen that is present here that facilitate the elimination of the ester, carboxylate ester unit here. So we end up with an alkene. So this is generally used for the elimination reaction. So final product is, this is the B. So that way we can easily see what is the overall mechanism for this reaction. Let us look at the next problem. So here the major product formed in the following reaction. If you look at the structure, it is highly complicated and too many colors and other things are there. So I have made it colorful simply because there are 4 different functional protecting groups are used in this reaction, and selectively only one of them is cleaved. So to easily figure it out what are the different types of group, I had given 4 different colors, but in the question paper you will not see all 4 different colors. This question was asked in December 2015. So we have a starting material. This is nothing but the, don't look at the big substituents that are present. Let us simply focus on a simple core of this molecule. So this is nothing but a simple carbohydrate derivative. Okay, the carbohydrate has multiple hydroxyl groups, and each hydroxyl is protected as a different protecting group. And when these are protected as the different types of protecting group, we are going to use the reaction with the DDQ. So this will selectively cleave one of the functional groups. So we do need to know what is the different types of functional group that are present and what DDQ can actually do. These 2 things, if you know, you can easily figure it out what is our product in this particular case. So the first one is the paramethoxyphenyl ether. So this is the paramethoxyphenyl ether that is shown here, and the second one is the paramethoxybenzoyl ether. So here this is ester. So this is the ester group, paramethoxybenzoyl ester is given here, and the third one is paramethoxybenzyl ether. So this is the paramethoxybenzyl ether. So here we have another extra carbon that is present here, and the last one is the simple benzyl ether. Okay, so these are all the 4 different functional groups that are present, and the DDQ selectively cleaves paramethoxybenzyl ethers only. So the moment you know DDQ cleaves paramethoxybenzyl ether, you can easily figure it out what is your final product. And in the starting in the 4 reagents that are given here, if you look at very carefully, they all have different functionalities, and we have to only look for where this orange group is missing. So the orange group is missing only in this particular case, so this is our final product.